Okay, Assalamualaikum and good afternoon. Okay, we have seen chapter 6.1 and 6.2. So now we will continue 6.3 qualitative influence lines. Yeah. So as we seen in the previous lecture for 6.1 and 6.2, we already know how to draw an influence lines. Yeah. So there are two approach where you can use tabulated values, or you can also use influence lines equations to draw the influence lines. Yeah. But in 6.3 now, we can use Muller-Breslau principles. So in this Muller-Breslau principles states that the influence line for a function is the same scale as the deflected shape of the beam when the beam is acted upon by the function. So what does it mean for qualitative? Qualitative means you can just predict the influence line, not in a numerical value, but in as a prescription, or in terms of prediction. You can just assume the shape, the shape of the influence line that will be achieved based on the loading applied to the beam or to the structures. In order to use this Muller-Breslau principle, you can consider beam figure 6.12a. For example, you have this simply supported beam. If you want to draw a influence line at AY, let's say you want to see what is the shear influence line for AY. So in order to draw the influence line at AY, or at support A, you change the pin support here as a roller support. So meaning that you give AY a positive support upwards. So based on this AY, you can imagine the beam will be deflect in a dotted line like this. So this is the deflected shape of the beam based on the AY load, or AY support. So this will give you an influence line. So meaning that the influence line for AY is based on the deflected shape here. So this will give a positive force AY based on the force acting upwards. So let's say we move to this beam. You want to see what is the shear influence line. Shear influence line at C. So this point C, you need to give or change it to a roller like this. Change to a roller like this. So means giving a positive VC, shear positive at C, and then you can imagine the deflected shape here, for the beam. So based on this deflected shape or the dotted line, then you can draw the influence line for VC. And then if the shape of the influence line for the moment at C is to be determined, then you can change the support by giving a hinge is placed at C. For example, here you have this beam, and then you want to see what is the moment at C, the influence line for moment. You can see here, influence line for a moment. So in that case, you have this C point change to a hinge like this. Then you give a moment here. Give a moment, then you can see, or you can imagine the dotted line here. what will happen to the beam or the deflected shape for the beam. So based on this dotted line, you can draw the influence line here. Yeah? So this is the influence line for this beam. So this is negative influence, a negative moment. This is positive and this is negative. Okay. So based on the Muller-Breslau principle, it shows that this qualitative influence line is using the principle of virtual work. Yeah. So I hope that you still remember what is the virtual work. Yeah? So for work is a linear displacement multiply with the force, or rotational displacement multiply with the moment. Remember, displacement must multiply with the force, and displacement rotational displacement must multiply with the moment. Okay, here for example, if you want to find this, let's say this, actually this is the displacement at A. If you want to find the AY at support A, so means that is equal to one unit force being given at this multiply with delta Y. So here the unit load does negative work is equal to negative 1 unit load given to the beam, to the point, at that point multiply with displacement. Why this one negative? Oops. Why this one negative? Because you give this one, unit point load going down, and this one is positive, considered positive because it's going up. Okay, so in that case you can have this equation. Okay, another example here, same thing. If you want to find internal shear, internal shear at C, just now at support, now here at point C. Okay, same thing, at point C you give a roller. So based on this roller, the simply supported beam will deflect like this. Okay, so means that the 1 unit point load multiply with delta Y must equal to the VC here, this equation. So this is actually based on the virtual work, if you still remember. And similarly to a moment here. So you have this, let's say you want to find the moment here, based on a unit, 1 unit displacement, or if you want to find the rotation based on 1 unit moment given to this point. So end up you will have the moment given to the beam is equal to delta Y, assuming that this is 1 unit. So all of these are based on the virtual work method. So the main point is that this Muller-Breslau principle indicates that the deflected beam has to be same shape as the influence line for the internal moment at point C. So it will be based on the deflected beam, and based on the deflected beam you can draw the influence line. Okay, now we move to the example 6.9 to see how to use the Muller-Breslau principle. Means that you can imagine based on the deflected shape, and you can draw the influence line. So here question 6.9, for each beams in figure 6.16a, sketch the influence line for the vertical reaction at A. Okay, here the first example, the first beam. So you have this beam. The question asks you to find vertical reaction at A here. So what you need to do is to change the support A to a roller. Yeah, you see here, a roller system. Change the roller system giving positive AY, yeah, going up. So when you push support A going up, then you can imagine the deflected shape here, yeah, the dotted line. So based on dotted line, then you can draw the influence line here. Okay. Another example, cantilever beam. This is cantilever beam at A. So you need to find influence line for vertical reaction at A. Okay. So change the feet support here. So this is cantilever. Change this to a double roller guide. Meaning you push this one with positive AY. Yeah. So when you push upwards, of course the beam will move upwards, but in a consistent line. Yeah. So based on this line, you can draw influence line for AY. Okay. And then the last one here, you have three support. Roller and pin. Yeah, this is pin, this is roller, this is also roller. So you need to find at A, this point. Yeah, so you can change this roller guide. Again, a roller guide is placed at A. So here, giving this positive AY, and then you have this deflected shape. So this deflected shape will give an influence line. Yeah. So you can see how similar the influence line to the deflected shape. Okay. Now we move to example 6.12. Determine this one is in page 245. Yeah? Page 245. Okay, those who has the e-textbook, you can turn to page 254. 254. Determine the maximum positive moment that can be developed at point D here. Due to a concentrated moving load of 16 kilonewton, uniform moving load 3 kilonewton, and a beam weight, this is self weight, yeah, self weight of 2 kilonewton meter. So concentrated moving load is like a point load, but it's moving. Okay, point load of 16 kilonewton. Okay, so positive moment at point D. So what you need to do is this, change to hinge. Yeah, when it said positive moment, moment means change to hinge. Yeah. Okay, so here, change to hinge and give moment, because the question asks you to get the positive moment. When you change this hinge, this point to hinge, give moment, then you can imagine the deflected shape. Yeah, so this dotted line show the deflected shape of the beam. So based on this, you can come out with an influence line, but of course you need to know what is this H value. Okay, so based on this H value, you have three types of loading, because you want to see what is the maximum positive. Yeah, maximum moment positive. Okay, so you have three types of load. (16 kilonewton point load), and then the second one is 3 kilonewton meter uniform distributed load, and then the third one is self weight. Self weight of the beam is 2 kilonewton meter. So when it says maximum moment positive, means that you need to put all the loading here in the positive area. Okay, so because here this is negative area, this is positive area. Okay, so when you want to find the maximum moments, means that all this must be placed here. 16 kilonewton, 16 kilonewton. So to get the highest value of 16 kilonewton for the positive moment, you need to put here 16 kilonewton. And then 3 kilonewton meter. So you can put along this line all the uniform distributed load. And then self weight 2 kilonewton. So this is self weight of beam. So you have to put all this 2 kilonewton. Yeah. So means that from here to here you have three kinds of load. 16 point load, you have uniform distributed load of 3 kilonewton meter, and then you have another one, self weight 2 kilonewton meter. Okay, so based on that you can calculate what is the MD. So how to get this MD is actually based on this. So you can see here, so 6 kilonewton point load is being placed at the highest influence line just now. So end up you will have this diagram. Then you can calculate what is the AY. So you can do section by section. Cut this portion first. You get the AY and BY, and then you do this another portion here to get this. So end up you will have what is the MD, which is based on this. The moment at D is 36 kilonewton meter. So all of these are based on the influence line that you have here. Okay. So another way that you can also get, based on because this solution is actually based on the Muller-Breslau. This one is based on the Muller-Breslau method, but you can also use this one based on the tabulated value. Means that you can draw a table and get the influence line, and that you will have the same influence line like this. Where this is H, this is H, by giving 1 unit at D. So this is D. You give 1 unit at D, then you can plot this influence line using tabulated value. Okay, so you can have this one, but of course you need to know what is H. So this H can get from this equation. Yeah. Once you give one unit, this one, then you can get what is AY, BY value, CY, and the E, yes, the support value. So once you have this value, then you can cut the section and get the MD here, the moment at D. So this moment at D is actually using this proportional triangular. Yeah? So you can have H is equal to 1.33. So this H value is actually 1.33. Yeah. So remember, to get the moment value at D, you can use the area. So this one. Yeah. The loading on the beam using the area and positive peak value of the influence line, we have this MD. So you can check your value here is still similar with this value by Muller-Breslau. Okay, so there are two methods. If you want to make sure that, or you want to check whether your value given by Muller-Breslau is correct or not, you can also check by using tabulated value. This one, yeah. Okay. So that's all for 6.3. Thank you.